Let's continue with ternary system for this week. But in this case, we're going to deal with tie lines, delta point, and plate point. So we're going to determine the composition of the conjugate solutions using titration, and then we're going to draw the tie lines and determine the delta point and plate point in the ternary phase diagram. We're also going to determine the amount of acetic acid in water-rich phase and chloroform-rich phase in a mixture of two-phase region of a ternary phase diagram using the lever rule. Now, last week we were able to construct the binodal curve, and I asked you to save the screenshot in PPT because we're going to make use of that for this experiment. So if we're going to consider again the partially miscible liquids, we can determine the binodal curve, or we can construct the binodal curve using the experimental data. We actually made use of the turbidimetric titration. When I say turbidimetric titration, the sign of the endpoint would be the sign of turbidity. Okay, so if we're going to consider a point inside the region of immiscibility, in this case, if we're going to consider this point, wherein you have the region of immiscibility, which is P is equal to 2, now you have two layers, and that could be separated. You could either have the upper layer. When I say upper layer, that would be the layer that would be of lower density. That's why it's in the top part. And then you have the lower layer that would be of higher densities. If you're going to consider again this point, you have the upper layer, which would have a composition equal to C, and the lower layer would have a composition that is equal to B. So each layer would be titrated to know the weight percent of A, and it would be plotted on this binodal curve. So for example, we have here this point. We just have to get the two layers. We're going to titrate each so that we could determine percent A. So if we know percent A, we can plot that. Let's say for the upper layer, we determine percent A to be equal to, let's say, this is 30. That's why we plotted here 30% of A. And then the lower layer, let's say, that is equal to 19. So we plotted here 19 in terms of percent A. So that's what we're going to do. We're going to look for different solutions inside this binodal curve, and we're going to determine those points in the binodal curve for the upper and the lower layer. So if we're going to consider that point S again, the upper layer would be C and the lower layer would be B. Now we're going to connect these 2 points, B and C. So that would be our tie line. So if we're going to consider many points inside the binodal curve, then we can create many tie lines. So in this case, we have 3 tie lines already. So different points in the region of immiscibility would mean different tie lines. Now at each point of the tie line, the composition of the upper and the lower faces would be determined. So just like for example, a while ago, we determined this point as the upper layer for this point, and this is the lower layer of this point. Let's say you have a point here, the upper layer would be this point, and this is the lower layer. Now, why I always look here as the upper layer? Because the density of water is 0.99 grams per ml, while for chloroform, the density is 1.49. So this is heavier. That's why this is the lower component, and this is the higher or the upper layer component. Okay, now we could actually determine the composition of these using the lever rule. So that could either be in mole fraction scale, so that is given by moles of component C over moles of component B, that is equal to the line segment AB. So we need to know what is the size of this line segment AB over the line segment AC, and we're going to make use of a ruler to determine that one. We're going to discuss that later on. And then you have the mass fraction scale. So you have instead of having moles here, what we need are just the masses. That's why it's in the mass fraction scale. And then after we created the different tie lines, we can extend these lines, and that would lead us to what we call the delta point. That is where the different tie lines would actually converge. Now from that delta point, we could use that to project a particular tile line for a particular point. For example, we have here a point. So from this delta point, we could create or we could draw a line passing to that point. So we could determine the lower face and the upper face for that particular point that we're considering. Okay, so again, from delta point, the tile line for a new point inside the region of immiscibility can be drawn. Also, you could draw a tangential line. So you have from delta point, you have a tangential line to the binodal curve, and the point we're in, or the point of the tangent point would be the what we call the plate point. So that is the tangential point. The composition of the two faces in this particular point would be the same. So meaning to say, the composition here of the lower layer and the upper layer would be the same. Where basically, you have the same composition for both layers. So take note that this particular point is not located at the maximum of the curve. The reason to that one, the tile lines are not horizontal. As you can see, they are inclined on the heavier component, in this case, component C, based on density. Now, how are we going to do the experiment? So the first thing that we have to do is to prepare different ABC solutions or the ternary mixture inside the region of immiscibility. So you have component A, which is acetic acid plus water, and then you add chloroform. Now take note, we're going to create 4 different 100-gram mixture. Now take note, in preparing the 4 different 100-gram mixture, the volume of the upper layer is equal to the volume of the lower layer. So we're going to mix that in a beaker. Take note, these are partially miscible, so you would expect that there would be 2 phases, the upper layer and then the lower layer. And then you're going to mix that, you place that in a separatory funnel. And then you equilibrate that. When I say equilibrate, you just have to stand that for 10 to 15 minutes. So you have the equilibrated mixture. After you have the mixture equilibrated, the next thing that you have to do is to separate that, and then you measure the density and you titrate. So you separate that, you separate the upper layer and then the lower layer. And then after that, you're going to measure the density using pycnometer, which you already learned in Phychem 1 laboratory. And then you also have to titrate that using the 1 molar sodium hydroxide. So the concentration of sodium hydroxide that we're going to use here is 1 molar. And that sodium hydroxide would titrate the acetic acid component. Remember, you have the acid-base titration. Now, so for the separation process, you're going to make use of the separatory funnel. So let's say this is the upper layer and then this is the lower layer. So what you need to do is just to open the valve, so that should be perpendicular to make it open, and then once you reach this boundary, you close so that you would not mix the 2 components. Okay, so what I usually do in this particular case, I want to get all of the lower layer, almost, rather, not all, and then once I only have here some of the lower layer, I remove the E-flask, I get a waste container, and then I let it flow so that the last drops of the lower layer would be put into the waste, and then the first drop of the upper layer will also be in waste, so that I'm sure that the 2 components are well separated. And then after that, I make use of the pycnometer to determine the density. So what you have to do first is to weigh the pycnometer, and you have to record the weight. And then you're going to place water, that is our standard. And then you record the weight of the pycnometer and water. And then after that, I remove the water and then make sure that it is dry. And then I place there the solutions that I'm going to measure in terms of density. So I would place the upper layer and then the lower layer. So again, discard the water, dry, and place the liquid mixture that you're going to measure the density. So in this case, I'm going to weigh and record the weight, and then that would be the end of density measurement. I just have to use the formula: density of the mixture, or the density of the upper or the lower layer, is equal to the mass of the mixture, or the mass of the upper and the lower layer, over the mass of water times the density of water at the temperature of the batch. In this case, we're just making use of the density of water that I gave you in the previous week, which is about 0.99704 grams per ml. Okay. Now, how do you calculate the mass of the mixture? Basically, that's the mass of the upper layer plus pycnometer minus mass of pycnometer. The mass of water would be mass of pycnometer plus water minus mass of pycnometer. So in this case, the mass of mixture would change. That could either be your upper layer or the lower layer for the 4 different mixtures. Then once you determine the density, do not throw the liquid. What you need to do is to titrate that one. Okay, so you get 5 ml of the conjugate phase, and then you add 30 ml of water, and you add 2 to 3 drops of phenolphthalein, and then you're going to titrate that until the faint pink endpoint. Make sure it's faint pink, not dark pink, because that is an override, and you get a minus for that. You know that. And then for the data analysis, what you have to do is to have the density measurement. So you have here the mass of the empty pycnometer, and then you have the mass of pycnometer plus water, the mass of pycnometer plus the lower phase, and then the mass of pycnometer plus the upper phase. And then after that, you're going to have the masses here. Summarize the masses here for the water, the upper, and then the lower phase. And then you get the density. How do you get the density? You use this formula. So you have the mass of, or the density of the mixture, it's mass of mixture over mass of water times the density of the water. In this case, use this density, 0.99704 grams per ml. So you have to get the average density if there are 2 trials. But most probably, I will just give you 1 trial for this one, because it's a theoretical one. It's not experimental. Okay, and then after that, you have the titration process. So you need to know the volume of the aliquot. We use 5 ml, right, in the procedure. So from the 5 ml, you have to record the final and the initial reading, as well as the volume used for the sodium hydroxide, because we need that for the calculation. So take note in our procedure. Let me go back to that one. We titrated 5 ml of the conjugate phase. So 5 ml of the lower phase and the 5 ml of the upper phase. And then what we need to do is do the calculation. So for us to be able to get the mass of the aliquot, the mass of A, and percent weight per weight of A, we need to do the following. So for the mass of A, which is the mass of acetic acid, we have the volume of NaOH used in the titration. We convert that to liters, and we multiply that by the molarity of sodium hydroxide. The sodium hydroxide that we use is 1 molar. So from here, you get the moles, and then you just have to get the mole ratios. 1 mole of sodium hydroxide would be equal to 1 mole of the acetic acid. So you already have the moles of acetic acid. You just have to convert that to grams using the molar mass of acetic acid, which is 60.052 grams per mole. So you already have the mass of A. How about the mass of aliquot? Remember, you have 5 ml of the aliquot. You just have to multiply that by the density of that particular aliquot. So we're able to determine the density of the aliquot in the density measurement. And basically, for percent weight per weight of A, that is mass of A over the mass of the aliquot times 100. Now you have different percent weight per weight for the 4 solutions, the upper and the lower phases for these 4 solutions. So for example, I have mixture 1 here. So I have, let's say, the percent weight per weight for the lower is, let's say, 10, and then the upper is 30. So I would just have to look at the binodal curve. So let's say this is 10, for example only, and this is 30. In this case, it's not 10, it's 19. So let's say this is 19 for the lower phase, and then the upper phase is 30. So I would just plot that in the binodal curve and then connect. So that's one tie line. So for example, in this data, let's say again, I will correct that if this is 19 and this is 30. So what you need to do, you plot the lower phase. This is 19 and this is 30, and then you connect. So again, the procedure would be plot the percent weight per weight acetic acid of the upper and the lower phase, and then you have to connect to create the tie line. So you have to do that for all the solutions. So we have 4 solutions. After you have the 4 solutions, you extend the tie line. So basically, you just have to use a ruler. In your case, since we are in the PowerPoint, you could use the different tools in your PowerPoint. You use the line, and then you extend that one until you reach the point where the 4 lines would converge. That would be the delta point. And then from that delta point, you try, let's say the delta point is here, you just have to create a tangential line so that you could be able to locate the plate point. Okay, so basically that's it. So that's basically the continuation of the first experiment. In the first experiment, we were able to create the binodal curve. In this case, we're able to create the tie lines and then identify the delta point and then the plate point. Okay,